point from Carroll was that apparent fine-tunings may be explained by dynamical mechanisms or improved notions of probability.
So there's two things there. One of them is he's got an actual case of the second one. So there's been a widely discussed case of fine-tuning where if you take the early universe and say how much stuff is there, how much density of matter is there, and you start changing that number, well, if you make it a bit larger, the universe recollapses. If you make it a bit smaller, the universe expands too fast and you don't get any structure. And there's been an argument put forward, which actually Sean's written about, and I think goes back at least to sort of some papers by Stephen Hawking and Don Page in the 80s. And there's been a bit of back and forward about this, but the basic idea is actually when we try to say what sort of universe is the most likely one, there's a reason for giving that the special case of it doesn't expand too fast. Actually, that it's called a flat universe. It goes at critical density. There's reasons to give that one at least more probability than the rest of them. So you don't just choose that number at random. And so what that looks like is, if we better understand the probabilities in our theories, maybe it'll turn out that things aren't fine-tuned at all. And that's a live option, and we have lots of cases of these numbers, and so let's just look through these cases.
It's definitely something we need to evaluate for each individual case independently.
So there's a couple of things to say there. First of all, when you look at the numbers that could be fine-tuned, it's really only that one which could be susceptible to that. And the reason is it's kind of a three-way tie. There's the early density of our universe, what it actually is. There's the number that life needs, and then there's this critical value that is the line between recollapses and expands very, very quickly, right? The critical density. And we see that our universe is close to the critical density, and also life is close to the critical density. And so there's kind of something to aim at. If you aim for critical density, you'll get life thrown in for free. It's precisely what we don't have for these other numbers. Things like the cosmological constant. It's not zero in our universe.
If it had been zero, then maybe that could have applied.
Maybe this argument might actually work.
But now that we know it's not, then
so clearly it's not the case that you can't have a universe which accelerates very quickly, because ours is one of those, and so that's clearly a possible scenario. And especially things like the mass of the fundamental particles, on a scale from 0 to what's called the Planck mass, which is the largest mass that our theories can currently handle, the fine-tuning range is in this really weird little section that's sort of 1 times 10 to the minus 17 does maybe 3 times 10 to the minus 17, whatever the numbers is, we look those up. And so...
nothing natural or special about that region, really.
There's nothing in the equations which marks those out as special. There's nothing mathematically wrong or mathematically different, or any reason from the equations you would expect to be in that range rather than any of the other
In fact, isn't it true that in some cases from quantum mechanics you would expect the natural particle mass for certain particles, like say the electron, to have been heavier, or things like there's sort of a naturalness problem already within
the best equations we have. If you sort of naively use them to predict these numbers, you end up with much larger values closer to the Planck mass, or at least closer to some larger scale,
which would be in the non-life permitting region.
So one of the problems there is that this improved notions of probability, it seems like that's a very specific circumstance to that one constant, which turned out to be quite nice. With respect to, he says, a dynamical explanation or a mechanism, and the answer is sure. What we don't know might overturn what we currently think we know. Fine.
Sure, that's true of all science, right?
Yeah. So the point of what we're trying to do here is not to say that we think God is better than all possible future explanations of the universe. So that's not what we're trying to do. We're not trying to put God up against all sort of scientific theories. The idea is really, suppose we'd finished physics and we were all done, right? It was all up on a board or something, and we started to wonder why the universe is the way it is. We might wonder about other ways it could have been. And, if we're trying to think about other ways the universe could have been, I think the best we can do is just take the best physics we have and see what else could have happened. And if better physics comes along, we'll do it again. But for the moment, we'll just do the best we can with what we've got. If you want to say anything about the way you would expect the universe to be on naturalism versus the way you would expect to be on theism, you've got to do something like this. You've got to have some idea about how the universe could have turned out. And this seems to be the most systematic way of doing it. So possibilities here are cheap, in particular because this is a probabilistic argument. Right? It's not an argument that definitely totally proves its conclusion. Right. With all, just about all probabilistic arguments, you can imagine the circumstances under which it would, in fact, not be true. Like it would be an unsound argument, or you can imagine the circumstances under which actually the evidence we have was a bit misleading. Actually, we thought it went this way, it goes this way. We'll get on with it. That's true of all probabilistic arguments. We'll deal with that when we come to it.